Hey everyone, let's do another daily Leetcode question. If you're new to this channel from the Chessboard Detect videos, I also do programming puzzle questions on a website called Leetcode. If that's not your cup of tea, feel free to skip this video and come back. For everyone who's still watching, let's get into it. Today's a fun one. It looks like we're doing a hard question, so let's start the timer over here in the top right. And it is number 1568. Minimum number of days to disconnect island. Ooh, okay. Islands are fun. We've done a couple island questions. I'll link them above too. So this sounds similar. So you're given an M by N binary grid, binary grid, where 1 represents land and 0 represents water. So a nice little infographic. An island is maximal 4-directionally connected group of ones. And so that means it's only connected horizontally or vertically. We don't count diagonals as connections. And the grid is said to be connected if we have exactly one island. Otherwise, it's disconnected. In one day, we're allowed to change any single land cell into a water cell. Return the minimum number of days to disconnect the grid. Okay, this looks pretty cool. I'm interested to think about how hard this is going to be. M by N could be a very large grid. Like, let's say it was all ones. Would it be a bunch of, would you have to like slice it vertically or horizontally? That's kind of what's going through my head right now. This example shows that you can break it by getting rid of all the horizontal and vertical connections. So 0, 0, and these two are not connected, so you now have at least 2 islands. What happens if you already have a disconnected island? We're only outputting the number of steps to turn it into to disconnect the grid. So if it's already disconnected, I guess it's 0 for the minimum number of days. And in this case, because this one required 2 cells to be changed, it's an output of 2. We need at least 2 days to get a disconnected grid. Change these land cells to get a disconnected island. The interesting thing to keep in mind is we don't care about which cells they are. We just need to know the number of cells that need to be changed. Oh, this is kind of a fun one. 1, 1, and 0, 0. So here the output's 2 because you have to, if you removed any one of them, it's still a single island, so it doesn't break into 2. So you have to get rid of both of them, but then there's no island, which counts as disconnected. Okay, that's good to know. Some questions to ask to the interviewer here is how big would this grid be? Can it fit in memory? Since this is Leetcode, the answer is yes. If the answer was no, we might have to do kind of interesting things like loading up the islands in chunks and looking at the boundaries. That would be a really hard question too, and this already looks hard enough. By the way, since we're doing a hard question, I'm not sure how long this video is going to be. You already know because you're watching, but this could take me forever. I might never solve this. Hopefully I do. Either way, we'll hopefully learn something along the way. M by N is max 30 through 1. Okay, that's good to know. And grids are either 0, 1, and okay. So kind of what's going through my head is thinking about how we might approach this. One thing I'm thinking about here is how much time are we in? We're still, 3 minutes and 24 seconds in. So we're still really early in the interview. I don't want to start trying to code anything just yet. I'm just trying to think about how I would approach this as a human. So the first thing I'm thinking about is how do you tell if an island is connected or disconnected? So the questions I'm asking is how to tell if a grid has one island or more. That's basically the same saying connected versus disconnected is equivalent to 1 versus 2 or more islands. How do you count the number of islands? That's similar to the last question we did. We could go down that path. I don't want to decide on that yet, but the idea there is some sort of flood fill algorithm, and the idea with that is you find the first island cell and you just fill it out until you have deleted all the other island cells. We could go down that route, and if you did that and everything is 0 at the end, you know you have exactly 1 island and it's valid. I don't like the idea of that because that will be a O of, well, actually it's only O of N, I think, because you're checking for the island and then you're just checking if there's more islands. That at least tells you if it's to check. So that's one way we can start this approach. And then the idea would be if we had to find a cell to remove and then check with the flood fill algorithm again to see if it's disconnected. That's not the way I think I want to go. I'm pretty sure, I don't know this off the top of my head, but there's like some sort of like min cut algorithm out there. And since this is a hard question, this might be relevant. I think if I could use Google, I would start Googling like a min cut algorithm. And the idea behind those is there's a way of kind of filling out cells in a grid such that you know where the choke points are, and you can identify and in this case count them. And if it's exactly 1 to break the sections into 2, then you know the answer is 1. Otherwise it's 2 or 3 or 4 or whatever. But what else is there? Just trying to talk out loud all the different things I'm thinking. I'm really hoping there's a trick or something here. I'm trying to think of something mathy maybe. Is there some sort of mathy solution we could do here? Could we like count all the ones ratio to the grid? Is that useful in some way? Because let's say the number of ones is a square. Like that's kind of interesting. So like think about like if you have a square of 1, 1, it's a 2 by 2 grid. You know you have to remove at least 2 cells to turn it into 2 cuts to make disjoint. Does that mean if you have a 3 by 3, then you require 3 cuts? Like for example, you have to do 0, 0, 0. That's kind of the way I'm thinking about this right now. Because then maybe we just need to count the number of squares in the image, because anything less than that would be less number of cuts, and so you only have to look for the worst case, which is the biggest cube or square. I kind of like that idea, because you can do that in a sort of like ON, maybe ON squared or less, O of n, where n is the number of cells type approach. This might be O of n. Before we go down further, let's think about what's the absolute ideal way we could solve this. In a perfect case, time complexity would have to be O of n. You have to look at every cell. I think that's true. Is there any way you could not look at every cell? I mean, technically, if you find 2 islands before you've gone through the first row, you don't need to check the rest. But in the worst case, there might be all an island or all empty except for the last 2 cells or something like that. So you have to do O of n ideal. Space-wise, maybe in a perfect world it'd be empty. So that's kind of our goal. We know we can never do better than O of n or O of 1 in terms of time and space. So let's think about 1, 2, 3, 4. I'm just trying to go down this path because I'd really like this to work. Otherwise we have to do some sort of weird like flood fill, find bottleneck. If I knew what the min cut algorithm was off the top of my head, I do not. That might be another way to go about it. I'm just hoping to find a trick here because I would have to hope they don't assume you know some arbitrary algorithm for this. I could look at the hints. I'm tempted. There's a lot of hints. Oh my gosh. Oh, it is a hard question. If you all are seeing something that I'm not right now, and you're just like, come on, Sam, sorry about that. This is how it goes sometimes. Let's see. So is this a 4? Let's think about this. Because you have to do here. But, you know... Okay, I do think I see... So here's what I'm noticing. I had to cut it in the middle, but it didn't say anything about the islands being equal size. So here I could cut it like, say, it's like a 3 cell. I could just cut it there, is what I was thinking. But then I realize you could also just cut it down in the corner, and you only need 2 cuts to do that, and then you have an island, because you're only horizontally and vertically. And if you, this is for a square. What happens if you have 1, 2, 3, 4, 1, 2, 3, 4? That one's obviously 2 because you could just do something like that. But if it was 3, and let's just add an extra 2 rows here. Can everyone see this? I'm not cutting off. Good. Okay. So like here and here. Do I have to do this? I don't think, because again, we have the same thing where we just have to look at the corner. Can it be that simple? That'd be really nice. Okay, if you aren't following along, what I'm thinking about here is the idea that there's always going to be an edge to an island. And if it's like here, it's this edge, the ones, and it could be even at the edge here, no matter where you are. And you can always cut the edge with 2 cuts maximum, because there's a limit to the size of the grid. It's not a wrapping around. If it was wrapping around, we'd have to do like 0, 0, 0 down this, like here, you know? But because it's not wraparound, we can just find a corner and cut it. So I think that means, and maybe that's why they're showing this. They're saying this is another option when it's in the trivial case of just 2 cells that you have to do 2 cuts. And then there's an even more trivial case of if there was a single grid cell, then you'd only need 1 cut, like that. Okay, I kind of like this. I think you need... Okay, here's my theory. And this may have been obvious to you from the beginning. If not, you're right along with me. So hopefully you're finding this interesting. I think this is the trick. Yes, okay. Maximum of 2 cuts needed, no matter what. Because you can always cut right there at the end, and a minimum of 0. So there's only either 0, 1, or 2 cuts possible, and that's it. So we don't actually, and we're what, 11 minutes and 42 seconds in? Great. Okay, so I think this is the trick. How do we, so I don't think we need to do the flood fill. Oh, well, we might need to do the flood fill to check if it exists, but no, actually we don't. Here's why. How do you tell if a grid is connected? Maybe you still need the flood fill. I don't think we need the min cut algorithm anymore. Count all the ones. Okay, the other thing I'm thinking about is how do you check the minimum number of cuts? You can count, you go through every single cell and you count how many neighbors it has, and the maximum number of neighbors a cell could have is 4, and the minimum it could have is 0, or, and you only check the island cells, and like here, each of these have 2 neighbors, all 4 of them, so you have to cut the minimum number of those, which is 2. Here, each of these has 0 neighbors, but you could also have a case like, let's just create this right here. If you have 1, 1, 1 like this, each of these has only 1 neighbor, so you only need, you know, it doesn't matter, like we humans know it's the center one, but it doesn't really matter that the answer is going to be 1 cut needed. So similarly, if this was a 1, 0, 1, you know, like some sort of island like this, this has 2 neighbors, this has 2 neighbors, this has 2 neighbors, but these have only 1 neighbor, so still 1 cut needed. And we don't know that it's over here, but that's just how it is. Does that break if I go here? 1, 0, 1. Here you still need 2 cuts actually. So that is correct that they're all 2. But here there's 1, and in fact there's 3 possible places that the cut is needed. Okay, so the logic that's going through now is this idea of iterate through grid on neighbor on island cells, count neighbors, and keep track of smallest number of neighbors, return that as the result. I think that'll solve it for us when we have exactly 1 island. But we also need to check that like this would actually fail in the case of, let's say, like 0, 1, 1, 0, 1, 1, and then 0. Let's just do that here. So these are, and then you could have, you know, you don't actually have to do this, but let's just make it so it's clear to see. So here we have 2 islands, and each of them has island cells that all have 2 neighbors. So it is technically already 2 islands. So, but this simple logic would tell us we have to cut 2 to break one of the islands, but it's actually already broken. So we do kind of need to do a flood fill first to check that all the islands are, that there's only 1 island originally. I think we can do that at the same time though, and not that it matters, they would still be O of 2 times n, which is just O of n, but I think we can solve it that way. So let's just simplify and keep track of our super cool insight. Flood fill to check one island, and step 1, yeah, this will be our algorithm. And I don't really have any alternatives. I talked about the alternatives: min cut, flood fill, remove at random. There's many brute force options here. Check again. These are all going to be harder, I think. The algorithm I'd like to go with is going to be this one, where we start with a flood fill to check for one island. If it's not, then we're done, return 0. If not, one island. Otherwise, we go to step 2, which is count neighbors. And this all takes advantage of the knowledge that this is very cool. I'm feeling kind of excited about this one because it is still a hard question, and I like being able to get, well, we haven't done it yet, so let's not get ahead of ourselves. We're 16 minutes in. That gives us enough time in an interview. I'd say at least 20 minutes, 30 minutes to go. So we'll do step 2 here, which is where we iterate through the grid. On island cells, count neighbors of each island. Okay. Keep track of smallest number of neighbors. So let's create this flood fill, and flood fill algorithm will just be depth first search, some sort of depth first search through the grid. So how do we do that? Depth first search. We'll start with the index I and j, and then I kind of want to do it with a copy of the island, but that would use up space, so I don't want to do that just yet. Let's just make it 2. Yeah, we can replace the values. So here's what I was going through in my head. Step 1 was you can do depth first search to flood fill in a couple of ways. One is create a copy of visited cells. This is O of n space though. You could zero out grid cells as you visit. This is O of 1, destructive. And we don't want to do that either. But we can instead turn 1 to 2, since we're doing in Python, to show visited. It isn't destructive because it's just turned into 2s, so that's totally fine. So that's what we'll do. Assume cell passed is island. So how do we want to do this? It'll be kind of stack memory-y, but that's probably okay. Let's create our neighbor offsets. Equals. There's a couple ways one can do this. I'm just going to do like left neighbor, right neighbor, and up neighbor. So left and right, and up and down. And so these will be our offsets for offset and neighbors. Actually, we could probably do it OX or OI, OJ, offset I and J, and then we can say DFS of I and DFS of J. And then we do a quick check if I is less than 0 or J. If I is less than 0 or J is less than 0. Or I is greater than, let's see, grid. This is a Python grid, not a NumPy array, so M is equal to grid length of grid, and N is equal to the length of grid 0. We assume that the grid is legal because that's how they pass it in. Yeah, M and N. So we're creating those two values in ahead of time. So if I is less greater than or equal to M, or J is greater than or equal to N, then these are out of bounds, return. And then we'll change this value to if grid of ij is equal to 1, grid of ij is equal to 2. Oh, actually, let's do it the other way around. If grid of I, j is not equal to a island cell, not island, skip, return. Otherwise, we know it's an island cell, so we set it to 2. And then we go through all the neighbors. And then after we've done a DFS on the first one, we just count how many, if there's any ones left. And if there is, it already has more than one island, otherwise it doesn't. So we'll go for M, for J in range N, if grid of I, J, this is not the cleanest, but I'm just kind of going through this the most straightforward way possible. Hopefully everyone can still see this. Let's pull this over so it's a little cleaner. Sorry if it's been kind of cut off for a while. So now if it's an island cell, DFS of I and J, technically we could just, yeah, and then we return break, and we want to break out actually completely if that's the case. So how do we do that? And there's like the, I think in NumPy that would be really nice. So you could do like npdar argware of if this was a grid, and that would give you the first index. That would give you all the indices of island cells. We're not going to do that because we're not allowed to use NumPy usually. Though this is a question to ask your interviewer. There's probably a cleaner way. Let's think about this. Could be this is pretty messy. I know. Sorry about that. So here we now just go through all the grid cells and see if there's any cells. Zero. An island. Already has disjoint island. And here the idea is, just to be clear, what it's doing is we go iterate through the array until we find the first index, then we flood fill that and turn them all into 2s like this. And then after that we iterate through the grid and look for any 1s, and if there is a 1 we know we have an island already, and that means we can return 0 at that point. So that was the logic that's kind of going on over here. Otherwise we have a single island. Now check neighbor counts. And that's how we can kind of do it here. So if it's equal to 2, or if it exists, in this case 2, we can say, because we've replaced all the 1s with 2s at this point. So we could just actually just say if it's not equal to 0, min neighbor count equals 2. No matter what, we know it's never going to be more than 2. Count neighbors of grid of I of j. We can actually do this in this. Well, let's make a separate function that does that. Let's do it this way. So for speed, we'd actually want to probably unroll this, but I don't want to do that just yet. So we'll say count neighbors of I of j, check if how do we want to do this? We'll say that neighbor I is equal to I plus O of I, neighbor j is equal to j plus O of j, if ni, and then count is equal to 0, if ni is less than 0 or ni is greater than m, or nj is less than 0, greater than or equal to be clear, or nj is greater than or equal to n, continue because out of bounds. If grid of ni nj is equal to 2, count plus 1. And we do that for each neighbor, and then at the end we just return the count. So there are probably a lot of ways to optimize this, but we'll start with that, and then we just keep track of count is equal to that. And then there's two ways we could, if count is less than min neighbor count, we can't autocomplete. Count min neighbor count equals count. And then at the very end, we just return that min neighbor count. Yeah. And I think that's all we have to do here. I'm interested to see how this does. Keep return smallest, so we don't need to talk about this here anymore. I'll keep this up. Actually, let's keep it down there and just kind of think through our approach. So we're doing two things. First, we are using a flood fill algorithm, depth first search, to count all the connected grid cells horizontally and vertically. Not count, change the values of all the island cells to a visited one that's equal to 2, just like that, not double equals, sorry about that. And we just go through all the neighbors, and if they're existing neighbors and they're an island, only if they're an island do we do that. Otherwise we skip them. And after that's done, we check through all the cells, and if any of them... Oh, and to do that we have to iterate through the cells until we find our first grid cell, and then we start from that point. And then after that we go through all of the grid until we find our first, until we find any one that's equal to a 1. And actually, if they're already 0, has island equals false. If grid of I of j is, if all of them are, if any of them are equal to has an island cell. That's one way to do it, and we could technically do that earlier actually. Oh yeah, let's just do that here. We don't have to do it multiple times. Has island is going to be equal to true. And then if not has island, return 0. No islands exist. So we can do that check there. That way we don't have to track it here. And so step 1 is we check to see that there's no islands. And if there's no islands, we return 0 immediately. For example, if m and n were 1, or if they're all 0, then you return 0. Otherwise, we check for disconnected island cells, and if there's already disconnected ones, then we can return 0 immediately. And then finally, we check through all the neighbor counts by counting the neighbors for every island cell, and we keep track of the minimum count, and that will be either 2, which is for a fully connected, or 2 or more. And in the better case, it's 1. And the moment we find a 1, actually, we can stop. So if count equals 1, return 1. We don't actually need to go any further. Return immediately is min, because the only other min would be 0, and that only happens if it's already disconnected. So we don't even need to keep track of this. That's another nice little shortcut. I should have realized it earlier. So return 2, we know they're all fully connected, or better. Yeah. Or they're all connected, 2 or more. And we know that that we can always do a max cut of 2. We can always disjoint the island with 2. So yeah, if this equals to 1, we can return 1 straight away, because the only better case would be 0, and that never happens at this point. It has to happen earlier. And this may be obvious to you. I'm just trying to talk out loud about my reasoning, because as you saw, I found a slight optimization here, I think. I hope I'm not making some egregious mistake right now. Let's see, what time are we at? We're at 30 minutes, so that's probably at the point where we'd start to kind of have our final answer. Let's think about, before we run the test case, let's just do a quick discussion about the big O of this. So technically, since we're doing depth first search in place, this will be O of n time, because there's only a maximum of n grid cells for n cells. This is n equals m times n. Actually, this is overloaded. Let's do lowercase for the sides. And O of 1 space, because we're doing in place modification. So that's nice. This is O of n as well, to iterate through this. We're only storing a couple of O of 1 space time O of 1 space. Similarly, this is O of n time O of 1 space, just iterating through the grid, checking for if any of them are disjoint already. Counting neighbors, this function itself is going to be O of 1 times space because we're only counting a fixed number of neighbors up to 4. We're summing up values, but this is a single thing, so it's still O of 1. Then this is O of 1 being done over n times n, worst case n cells. And so that means that our final answer should be O of n time and O of 1 space, which I'm very excited about. If this works, there could be off by 1 errors, so on. In the interest of time for this video, and also my sanity, I think it's time to do some test cases. So let's try running this. Let's quickly think about how this would do on this one. Can everyone still see? I sure hope so. Good. Okay. Let's try running it and see what we get. This one is 011, 011, 000, so that'll be something like this. Let's just think about what it should be, because this is actually what you'll be doing with an interviewer. I know you want to just run it straight away, but we don't get that luxury in interviews all the time. So we'd expect this to be a minimum of 2 cuts. That's the same as the description, this one right here. So I would hope the answer is going to be 2. And then this one is 1-1. Will that be 2? Actually, that's a good question. No. That's a special case where I would have given the wrong answer here, because I would have seen these have only 1 connection each, and it would have returned a 1. But that is incorrect because it's 0, 0. So good thing we checked that. We have a special case where if m or n is special cases, we have some special cases. Special case, if m or n equals 1, there's a couple of ways this could go. Like, let's just say we had something like this. That requires at least 2 cuts. But if this equals 2 cuts. But if we had something like this, that's equal to 1 cut. And then if we had something like this, it's 0 cuts. So we have a certain special, and that applies vertically as well. So let's think about this. I think we can apply the same flood fill logic. Where we only need to do a flood fill check and also count the number of island cells, create some special checks. So we have our m and n here. If m equals 1 or n equals 1, special case. This is if sum of, let's just say if m equals 1, if the sum of grid, the sum of the grid, the sum of the grid is equal to 1, return 1, count. Total island cell count equals that. We have some special cases which we can take advantage of. If the island cell count is equal to 1, we return 1 directly. If it's equal to 0, return 0. we can do that straight away. Otherwise, we need to do a flood fill check as usual. We can count neighbors. Actually, there's no point counting a neighbor because kind of what I'm just thinking out here is if we just need to check for this case. That's all that's left. We're doing this. We've already got this one, and we've already got this one. And it doesn't matter if it's horizontal or vertical. So we've covered these two with these two cases, but we need to check for this versus this, and we have to do a flood fill for that. But then after that, we don't need to do any of the other checks, like counting neighbors, because we already know the answer is 1 at that point. So maybe what we do is we put in we do the check for if m and n. So we do the depth first search over here, and if it has an island, return true. Sorry, if it doesn't have any islands, that doesn't really need to do that, but it's fine. But now we can just say, and check for any disconnected cells, it'll return 0 in that case. But now after that, if m or n is equal to 1, just return 1, because we know we have a single island on a string vector. And there's only ever going to be 1 to delete that. Yeah, okay. A little messy, but sometimes these hard questions are like that, and it's good to kind of talk this out loud with your interviewer. I feel relatively good about this. Let's find out. Please work. I really hope so. Run. Come on. Oh, runtime error. Listen to C's must be slices. Where are we looking? Line 52. Oh, right. This is, you may have seen this already. That is me thinking in NumPy world. So let's get rid of all of that. I think 1, 2. Do I do it anywhere else? Yeah, I do it basically everywhere. Sorry. There. Okay. Let's try that again. Okay. One more time. Line 15. What am I doing wrong here? Oh, we're not allowed to do sum of grid? Right. Okay, that's fine. That's fine. We can do it the hard way. For row in grid, sum of row. And then we just do the sum of that. I think that's the way you do it. For row and grid, the sum of those values, and then otherwise the sum of all of that together. And this will just be a O of n. Technically, well, it's an iterator, so it doesn't store any extra values. Wrong answer on this one. Output was 1, expected 2. Special case when m and n are equal to exactly those values. All right, so I see my mistake now. So basically I need to, I was hoping I could do a little cleaner than this, but the special case is that when there's exactly m or n is equal to 2 and the other is equal to 1, and we are guaranteed that they're never empty, right? Yeah, it's at least 1. What we can do is do a special case there where we just check if it's equal to those. So what I had hoped was the case was like here when they're connected like this is 2 cuts. You know what I do realize is that the number of island cells will actually affect the final answer too, even if it's not m or n is equal to 1. So we'll do that count first. If island cell count is equal to 1 or 0, that's always going to be 1 or 0 in those cases. So it's not even a special case for when m or n is equal to 1. But now if m equals 1 and n equals 2, or m equals 2, this is kind of a hard-coded thing. I know it's messy, and n equals 1 and island cell count equals 2, return 2. Special case for 1, 1, something like that. Type grids. Though it's technically true for even a larger one. So actually, yeah, if m equals 1 or n equals 1, yeah, okay, return 2. Actually, if the island cell count ever equals 2, it's not always the case. Actually, this is not accurate. It's only when it's a single connected island. So here we have to still do a check to see if there's multiple islands exist already. So now, actually we don't need to do this check anymore because we have already done it in the beginning. We've done it up here. So yeah, island cell count is equal to 0 or 1. So here is the special case where if we have a single island and this is not true actually. This only is true if actually, yeah, if m or n is equal to 1, if island count cell equals 2, return 2, elif island cell, otherwise we return 1. Yeah. So the idea here is like this will be like a 0, 0, 0, 0, 2, 1, 1. Actually greater than or equal to 2. It doesn't really matter how that goes. Oh, if it's exactly equal to 2, then it's 2, otherwise it's equal to 1. Because now if you have the same thing, you only need one cut to break it into 2 islands. So if this is 1 like that, it doesn't really matter where you cut it, but you only need one cut to do that. So that'll fix that case, where if m or n is equal to 1. Yeah. And why can't the counting neighbors do that for us? I would have thought because there's only one neighbor for each of these. These each have only one neighbor, but you have to remove both of them. That's the only reason why. So technically you don't even need this because this will get there, but it's a little faster that way. Let's try running this and see how that does. I really hope this works. Yay, past those 2 test cases. We're about 46 minutes in. Let's submit it and see how it goes. I'm cautiously optimistic. Oh, wrong answer. Output a 2 and it should have been a 1. Okay, so what's going on here? We have this specific test case. Let's copy that and have a look at it. That's okay, we're on the path. Oop. Alright, so we have a disjoint connected islands, disjoint but connected by 1. This has 2 neighbors, but technically can be removed. Oh, so my original thesis was wrong. So I made a mistake here, as you may have already known. Now I know finally too. In this case, you only need 1 to disconnect these 2 islands, not 2, even though it has 2 neighbors. So it's actually -1, I think. Because here, 1, 2 neighbors. Huh. Oh, if it's horizontally connected, that's different than vertically connected. That's not true either, because you could create a case where this is just a 1, but because it's vertically connected, could you do this? These each have 2, this has 2, but no matter what, if it's only horizontally connected, okay, So I think we can fix this. It's about being vertically or horizontally connected, and if it's only vertically or horizontally, it takes 1 cut, but if it's side by side, that counts as 2 cuts. Except in this case, it's technically 1. So here's the one that's oh, I realize it's 1, 2, move. Oh my gosh, weird. Three, two, choose one. So if I think 2, that should be 1 in this case. So we haven't got it from just the counts. I want this to be a 0, and that disconnects them. If you have zeros on at least 2 sides, does that mean something? Not exactly, because you have zeros on this one. Can you look for specific patterns, maybe? Is that one way to go about this? There's probably only a couple ways you could have these special cases, like horizontally, vertically, and these kind of specific edges, like that. Could we enumerate all of them? So like, let's just quickly think about it. Because what I'm thinking is if you can just check for any of these special cases, you can... Actually, that might cover most of the cases. I'm feeling kind of optimistic about that.
2 hours later.
No, that's not the right way. I'm not entirely sure what to do at this point. Ugh. I guess when I look at this one, can you look for a row or column that has... Could we look at all the neighbors rather than just the 4 cell? Count water cells in 8 grid. In all 8 neighbor spots. If 3 or more, only 1 cut needed. And is that true? Can you create a situation where you can have at least 3 spaces and cutting you does not? Yeah, you can actually. This one has 3 water cells next to it, but removing it does not cut the island.
A few moments later.
Not sure. We're running up on 55 minutes at this point. Well, let's have a look at the hints. Let's see if that can help us. Return 0 if the grid's already disconnected. Great. Return 1 if changing a single land to water disconnects the island. Otherwise return 2. Okay, we got that. We got to that. We can always disconnect within at most 2 days. Feeling a bit lost at this point. There must be a way that's not just checking all of them, right? What am I missing? It might be really simple. Maybe we did have to go with that min cut algorithm. Okay, before we get completely like stuck in the weeds, let's just pretend we have enough time. I don't want to waste the interview entirely. So what we can do is think about brute forcing this. The only thing we're trying to check for is if a single island could be disconnected, and if so, then we have a disconnected set of, like 2 islands from 1. Otherwise, it'll always be 2. So we're just checking for the 1 case. We can do that by brute forcing, and the way we can do that, and I really didn't like this because I was hoping to find a O of n time and O of 1 space solution. Ideally, I think what we'll have to do is check for every island cell, remove it temporarily, count DFS flood fill, the grid, and see if we have disconnected or not. Nope, sorry. So this feels really wrong, and there's probably a better way to do this. Basically, we go through every single island cell. Like we start with this first one, we turn it to a 2. We then do a flood fill, ignoring 0s and 2s, and then we can convert those. Like let's say, actually, let's convert it to 3, and check for if there's any 1s left, and if so, we have a single. We know that we can do it with the 1. Otherwise, we turn this back to a 1, turn all the 2s back to a 1, and continue. Yeah. So all the values are 2 at this point. So, and then we do that. And if yes, return 1. Otherwise, continue. And then finally at the end we return a 2. So that's kind of what we'll have to do. I I don't like this, and this will be a O of n squared solution, I believe, because we're going to have to go through for every single island cell. We're going to do a flood fill on it time. Technically still O of one space if we do it in place, so that's good solution this way. And I don't like it, but I think we need to solve the problem, so we don't really have a choice. How do we do that? We're going to have to do a special case for here, where check every island cell, disconnect, and see if island disjoint. This will become O of n squared time and O of one space. I'm pretty sure the disjoint, there's some sort of min-cut algorithm that would do this faster than O of n squared. I just don't know what it is off the top of my head. Please let me know in the comments if you know of it, actually, off the top. If you had or a way to come up with it straight away. I'd love to know of different approaches to solving this. I'll put in the description as well what I'm thinking about and whether it applies here or not. I'm pretty sure it does. There's some sort of min-cut algorithm that can do this, what we're about to do, much more efficiently. So let's try this. So for every single, let's just change private grid. If it is, then just set it to 1. Let's just start with that. Super messy, I don't like it, but we're just trying to go fast. So for every single one, we're going to say if it's equal to, if it's 1, we're going to just set it to 2 now. 3, let's say. And then we'll do DFS, actually here. Let's make sure. If it's not equal to 1, we skip it. And otherwise we set it to 2, which is perfect. That's what we want. So we'll do DFS of I and j, and then break. Say done equals true. This is probably a faster way to create this double for loop. I just don't have it. Actually, I do. I'll come back to that after we're done here. If done, break. I'll talk about that in a minute. But first, let's just say we're going to do DFS here, and now we'll go through every single one. And then, if any of them is equal to 1, we return 1 because we have disjoint island. Okay, we're at an hour and a bit. It's a toughie for me. Okay, so what I'd like to do is let's first create all these island cells, and let's just find them straight away first of all. So let's do it here. For say island cells dot append, I believe, ij. That's how we're going to just create the island cells. And then we can actually, instead of doing the count, we can do that here. This does create new memory, so this is O of n space. Yeah. You know what, I think it'll still make for a fast algorithm, and it's barely storing very much, so fine, I won't do it. I'll come back to that. And then the idea is you could iterate over this island cells for ij and island cells like that, and then you have a single for loop which you can break out of. So let's not do that just yet, just because I don't want to create O of n space. So if grid ij not equal to 1, continue, otherwise it's an islands. Let's create a function, is what I'd like to do, actually. Def check disjoint for a given I and j. So step 1 is we want to reset island values to 1. We can do that. Over over here. Sorry, down here. Let's call this KI, KJ, just so it's special. So reset island values to 1, if they exist, any non-zero. And then we'll do the rest of this. Return true, otherwise we return false. This will all be within this function. Now we don't need to do this loop here. We just check disjoint of k of I and k of j. So what we'll do is set k of I, k of j is equal to special disconnect value. We'll do DFS off the I, j. There we go. That'll just keep track of where the first island cell is. And actually we could do that once at the beginning. So let's just do that out here. And in fact, we've done that already. Trying to see if we could do it even earlier, but I think it'll make sense to do it here. So we're just keeping track of the first island cell once in this algorithm earlier on, and we can use that later on down here, so we don't have to do it every single time. We'll do DFS there, and then we check for disjoint islands. And if it's so, then we return true. Actually, you know what we can do? Then we can set it back. We'll set this back to 1. And what we can do is initialize this first in the beginning. So we'll set this grid k of I, k of j is equal to 3. Set ki, set check cell back. Return true that that was a disjoint island. Otherwise we return false, and we're gonna have to do it regardless back here too. DFS turns everything to 2, so actually we do need to reset. And this isn't the most efficient. Actually set it to 0. We don't need to do anything special there. And we'll set it back to 1. Water cell temporarily, that's a little easier. And then we set it back to 1 before we return. We iterate through this, we check for non-zero. If so, it's equal to 1. We could make this a quicker, smaller loop later on. And then now the special part is here. We do a iteration through the whole list. Check for special disjoint cell island cells. So for I and j, if it's a non-zero, we'll do, we should first reset everything to 0 just to be clean, and that's how it starts. We'll do check disjoint ij there. If check disjoint ij, return 1. Otherwise we'll return 2 at the end, but we have to check every single non-zero island cell. All right, let's test this on the test cases. We copied over our wrong answer one, I think, so let's try running it on these test cases. Still wrong, oh, wrong in the first one now. Bugger. I hope we're recording. Yep, still recording. Okay. So what happened here? We returned 1, which I assume means that we thought it was a We got true. That happened here incorrectly. Oh, we don't want to reset to 1 yet. We do that once here at the beginning of each one. Then we make a water cell 0. That way we don't actually have to do it here. DFS turns them to 2. 2s. Flood fill. Then it checks for destroy now if any of them is 1. Grid of KI, KJ gets set back and we return true. So now we have 1s and 2s. When we reset, all the non-zeros become 1s. Okay, let's try that again. Still wrong. Very frustrating. This will be, this is the O of n squared time of 1 space. Why is this returning 1 for this case? So basically like the description. So let's say it's setting this to 0, then it's just doing a flood fill through this, which should be all 2s. And then it resets that back to 1. Okay, I think maybe the case is what's happening here is it's trying to DFS in the first island cell. And if the KI and KJ is the first island cell, then it'll incorrectly DFS. It won't do a flood fill or anything. So we actually have to check for the first island cell manually, which is quite frustrating. So we don't do this anymore, unfortunately. A little cleaner, that's fair. I think there's probably a cleaner way to do this, but here we are. Alright, so it finds that first one, does the flood fill, moves on. If there's any island cells, returns a disjoint island, that there's a disjoint island, true. Okay, I think that's what we need to do, and that'll cover that case. Alright, past those cases, including our special one. Let's try submitting. Alright, we're... Hope for the best. Come on, please. Yes, accepted. Oh, I'm so happy about that. We did go a little bit over time. We're at an hour and 15 minutes, let's say. But we got it, and you know what's really nice to see is that it's in the bell curves. It's one of the faster ones. Looks like we could do a little more optimizations. I'm almost entirely sure these ones are just cheating, where they've just memorized all the answers, like Leetcode does this often, so let's ignore those. But these are real algorithms. We did it quite a bit more efficiently than this bundle. I think that's because we are not using any extra space, which I'm pretty happy about. So we have come up with a solution that is O of n squared time and O of 1 space. And you know what? Probably not the worst case in this algorithm, it looks like. I think there's some optimizations that you can make down here. We'll look at that in a second by just kind of optimizing how we look through these for loops. Like, I think you could clean this up a little bit. I'm just really happy we got this. Oh my gosh, this was kind of a slog. I don't know if it was for anyone still watching. This was an interesting one. I'm really happy we got to the end of it finally. I think could have saved myself at least 10-15 minutes if I just thought, at least 20 minutes, if I just accepted that we might have to do a brute force solution. I was trying to be too clever, I think, by just counting the neighbors. The good news is when you're talking out loud with an interviewer, they'll kind of challenge you on some of your assumptions, and we'd get to these challenges a lot quicker. I don't think I would worry too much about making that mistake. With an interviewer, the important thing is they kind of challenge you on it. You find out that you made a mistake, and then you, kind of like we did here, we think our way through the solution. We accept that we might have to do a brute force. Maybe there's something more optimal here. It might be as simple as this specific algorithm. I can't remember. Yeah, let's think about it. Some minor tweaks and optimizations. I would love to unwrap this double for loop and do something a little different with, like, if you kept track of what the island cells were, because then you don't have to check through every single grid cell every single time. But then you're storing the index of every single grid cell, which means it's no longer O of n, O of one space. Turning this into a NumPy array, you could do all sorts of fun, like argwares, which technically do that, but it's a lot more optimal. You could do some sort of ravel, unravel index thing. I'm trying to think of any other. There might be some minor optimizations which save you time where you can kind of combine some of these loops and so on. But in terms of building an algorithm and setting it up, I think this is a reasonable way to do it. It's not my favorite. I think there are maybe some edge cases here and there I'm missing. Please let me know. I think with more time, we could probably clean this up and combine some of the stuff. I wouldn't worry too much about that. That's not often critical in an interview, especially for I'd say a hard type question. It's more about working your way through thinking about all the edges. I think we did a good job of identifying some of the core concepts, like a maximum of 2 cuts. I think that was the critical key. This would have been, you know, O of n cubed otherwise. I think an O of n squared solution is not the worst. Let's have a look at what this solution was. Yeah, they do DFS, a little bit cleaner this way. They unraveled that loop. I think that's smart. I forgot to actually suggest that. Components, that they keep track of the counts as well. Or they do the counts for every single grid cell. Let's see. If grid is 1 and not visited. Oh, they create a whole, so here they've created a storage array, so they're not using O of 1 space, but that's okay because it does speed up the time. And then for every single one, they call this disconnection thing. So yeah, they're doing the same thing as us. They're using extra space by storing this visited grid, which I think is a good call, honestly, if space is not important. I kind of arbitrarily tried to optimize for O of 1 space. I think that probably hurt me in terms of developer time and time in this thing, but we got pretty good. I feel pretty good about where we got. I like this too. This is quite clean. I think it's good to kind of talk it out with the interviewer. Let's have a look at another one. Okay, this is closer to ours. They also use a visited grid cell. So again, I think this is a key point here, whether or not you want to use extra space. I arbitrarily chose not to use extra space and try to do it in place, and that caused a little bit of extra headaches for me, which was not strictly necessary. Okay, otherwise 2, 1, yeah, this looks about the same. What about these slower ones? What happened here? They do kind of what we do, but they also create a stack. Interesting, and they pop and push. They try to do they do DFS iteratively rather than recursively, which makes sense, you know, if you especially have stack memory limits. So this is also a very valid solution for a different type of problem. Say you had this running on a Raspberry Pi with limited stack memory or something like that. Very cool. All right, I feel really good about this. I'm really happy with where we got to in the end. I hope this was interesting for everyone watching. I had a really good time with this one. It did take us a while, so there is that, but I think it was pretty fun, and I hope it was interesting for everyone watching. I'm working on the next Chess Detect video. It'll be basically what I'm trying to do is I use Blender, and it's still new to me, but it's a lot of fun to make a higher quality chessboard and pieces data set. So stay tuned for that one. I think it'll be kind of fun. It'll be interesting to see if making a better higher quality synthetic data set results in better machine learning model results. I think the answer is going to be yes, but the question is how much and is it worth it? Either way, see you all next time, and thanks for watching. Cheers.